Hello and welcome to a series of short videos about the three most important laws in circuit theory. Ohm's law and the two Kirchhoff's circuit laws, Kirchhoff's voltage law and Kirchhoff's current law. In this talk we'll be looking at where those laws come from, what they mean, a few examples of them, and at the end why they don't always work, and how to spot when you can apply them and when you can't. In this first chat, we'll concentrate on the first of these laws, Ohm's law. First, a couple of basic concepts. Voltage can be thought of as a kind of pressure. You can imagine charge being pressurized, just like the air is pressurized in a tire or inside a balloon. Current is the rate of movement of charge, the amount of charge that passes one point in a circuit in a second. You can think of that like the rate at which air is leaving a tire out through a small hole, or a small hole in a balloon will gradually deflate the balloon as the air moves from the high pressure area inside the balloon to the low pressure area outside the balloon. And charge in circuits works in an analogous way. The charge is always trying to go from an area of high voltage to an area of lower voltage. Right. Some experiments were done in fluid dynamics long before anybody had thought of electronics, and in particular looking at the rate of flow of fluid, water, say, through lengths of pipe. And it was discovered that the rate of flow through pipes was proportional to the pressure difference across the pipe, the difference in pressure of the fluid at one end of the pipe and at the other end of the pipe. Exactly the same thing turned out to be true in electric circuits. And this is based on the experiments of George Ohm, who famously came up with Ohm's law, which said pretty much exactly this. In a conductor, the current is proportional to the voltage difference across the conductor. Whereas originally the law was specified for conductors, these days we apply it to resistors, because we know that it doesn't actually apply to everything which can conduct current. But it does apply to a very common electronic component called a resistor. We can check this out using a simulator. Here we have a circuit with a 12-volt source here, sending current down through a resistor to ground, which is at 0 volts. And we're measuring the current through the resistor with this ammeter, and the voltage across the resistor with this voltmeter here. So this circuit has 12 milliamps flowing down through a resistor with 12 volts across it. If we plot that point on this curve here, this graph would appear there. 12 volts corresponding to 12 milliamps. If we change the voltage across the resistor, maybe we halve it down to 6 volts, then the current halves as well to 6 milliamps at that point there. We could say at 9 volts across the resistor, 9 milliamps goes through. At 3 volts across the resistor, 3 milliamps flows through. And all of these points appear on a straight line. You can build this simulation yourself and check that it is true. For any voltage across the resistor, the current going through, plotted on this graph, would lie on this straight line. And that is what Ohm's law tells you. The current is proportional to the voltage. Now, since we have Ohm's law, that tells us that the current through a conductor is proportional to the voltage difference across the conductor, the difference between the voltages on one side of the conductor and the other side of the conductor. Say V1 up here, V2 down here. That's the conductor, the component that we're interested in. Delta V would be V1 minus V2. With any proportional expression like this, we can always write it in the form that the current is equal to some constant of proportionality times the difference in the voltages. For historical reasons, the constant of proportionality in Ohm's law is 1 over R, where R is the resistance of the component. And in honour of Ohm, the units of resistance are ohms. Rather than writing current, we usually use an I for current, and voltage difference and resistance in this form. It's more common to write Ohm's equation in this form. V equals I times R. Just multiply up both sides by R. It's a neater way of writing it. You don't have to worry about 1 over anything. But the original Ohm's law was that the current is proportional to the difference in the voltages across a conductor. One other thing that it's worth noting at this point is that the current always flows from a higher voltage to a lower voltage. The way I often advise people to write this is if you've got 2 points in your circuit, maybe 1 here and 2 there, then remember that Ohm's law is delta V 1, 2 equals I 1, 2 R. Delta V 1, 2 is V1 minus V2 equals I 1, 2 R. The 1 and the 2 are in the same order. That means that V1 minus V2 is I 1, 2, I 1, 2 being the current that flows from 1 to 2 in this direction. So the current is flowing that way, from V1 to V2. So a very common problem when you start doing circuit analysis is getting the voltage difference the wrong way round on components. This is a convenient way to make sure that you always get it right. Right, that's all I wanted to say about Ohm's law at the moment. Next one of these little talks will be some examples and talking a bit more about this concept of ground.